All right, here we go with the practice exam 3 for Math 114 trigonometry. This is the fall semester of 2003, in case I end up reusing one of these videos later in a different semester, because sometimes that happens. But any information that I give specific to the next couple of days is referring specifically to the fall semester of 2023. Did I say 2003 a minute ago? I did. I love that for me. Okay, yeah, 2023. At least got the last digit right. That's always the hard one. Cool. Let's start this review. Okay, so I can say that on this exam, we have worksheets 9 through 11. I mentioned on Monday that it was probably worksheets 8 through 11. I was wrong again. It is just I meant to put worksheet 8 on here, looked at the exam, realized I didn't put anything from worksheet 8 on the exam. So it's just 9 through 11. It is only inverse trig stuff. We shouldn't run into anything from like secant, cosecant, tangent, cotangent, those graphs. I ended up not putting them on this exam, despite the fact that I meant to. Oh, well. So just, again, 9 through 11, just inverse trig, which is fine because there's plenty of stuff for us to talk about in just those worksheets anyway. So first problem we're going to talk about, the simple harmonic motion model of a spring is given by the equation D equals the thing you see on the screen. D is in inches, T is in seconds. Find each of the following three things. So quick recap on simple harmonic motion. Anytime you see an equation that is just sine or just cosine with no shifting in it, that's what we're going to consider simple harmonic motion. And it's so simple harmonic motion is just the standard sine or cosine wave function. And we might transform that a little bit, but not a lot if we want it to still be simple. So this is simple harmonic motion. I don't really anticipate that's a question I'm going to ask, but in case it was, there you go. We want a few things: the maximum displacement from rest, the time required for one oscillation, and the frequency. And we're going to want to include units on these answers. Right, so if I go to highlight a couple of things that I thought were important with the correct units, and let's go from there. So each of these questions are asking for information that we have previously seen back in like worksheet 6 and 7. When we did graphs of sine and cosine, they're just going to use a slightly different name for them. So if we're talking about the maximum displacement from rest, that's just a fancy way of asking for the amplitude. So I want the absolute value of A. In this case, it's the absolute value of -8, which is 8, is the numerical answer, and I should attach units to that. If I'm talking about displacement, that's a length. So we should be measuring that in inches. Since we were told inches are right there. Up next, we want the time required for one oscillation. That is another fancy way of just asking for the period. Sometimes we use capital T for period. So 2 pi divided by B, which is 2 pi divided by 6 pi, which simplifies to 1/3. So our period is 1/3 of a second. Because again, we were told T, time, measured in seconds. And the period of this kind of a simple harmonic motion is generally in time. So seconds, minutes, hours, something like that. Oftentimes it's seconds. And lastly, we want the frequency. This was the one new thing. But the frequency of this object, well, the frequency of any object is just the reciprocal of the period. So 1/1/3, or the reciprocal of 1/3, which is 3. And then the units for frequency. Oscillations or revolutions per unit time. So this one might be oscillations per second. Or specifically, if we're looking at per second, we could call this thing 3 hertz. So the hertz unit is an inverse second unit, or a reciprocal of seconds unit. So hertz will only work if we specifically are measuring our time in seconds. Hertz doesn't work if we're working in minutes. We don't have a special unit for per minute or per hour. We do have a special unit though for per second, so hertz is there. I would take either answer on the exam. 3 oscillations per second or 3 hertz, or 3 just per second also kind of works. 3 times seconds to the -1 power. Revolutions per second, anything like that. So pick your favorite unit and use it on the exam. Where do I get oscillations per second from? So the frequency is measuring the number of times that the cycle will complete within a specific amount of, within like a unit of time. So because our time units were seconds, the frequency is measuring the number of cycles that this thing will complete in 1 second. And the name that we usually give to those cycles is an oscillation, or that's one of the names that we give to a cycle. So we could call it an oscillation, or we could call it a revolution. There are probably some other words, but those are the 2 most common. And it's per unit time. So these are oscillations per second, meaning this thing will complete 3 cycles or 3 oscillations in 1 second. Hi.
Say it was like 1/3 minutes.
Yeah, sure.
Would the frequencies for the label, did you put oscillations per minute instead of per second?
Yes, that's correct. So the question was, just so that I can get it to everyone and maybe someone watching the video, is that if we instead measured time in minutes, so that our period was 1/3 of a minute instead of 1/3 of a second, then the units for frequency would indeed be oscillations per minute, or RPM, if you wanted to go with that. I guess we do have a kind of unit for hertz and minutes. But yeah, it's our frequency and our period should have somewhat matching units. Yeah, it's the unit itself. Yeah. All right, cool. So that was that one. Up next, we get a word problem. All right, so a toy rocket is going to be launched from the ground toward a big tree on the other side of a privacy fence. If it's 21 feet from the launching platform to the base of the fence, and the fence is 9 feet tall, what is the minimum angle of elevation in whole degrees so that when the rocket is launched, the rocket will clear the fence? So I'm going to draw the ground in. We're aiming this thing at a tree. So maybe I should come over here and draw a tree. Hey, don't be like that. Stop it. Okay. Draw ourselves a tree. Let's see what's a tree look like. Kind of like that. Some green leaves. Hey, look, a tree. Okay, and then we also need to put a fence in here. The fence is actually the important part. Hey, stop it. 90 degrees. There we go. Fence, be some vertical line. And we are going to launch our toy rocket at this tree. Some other labels that we probably want to put on here. The privacy fence was 9 feet tall. We are 21 feet away from the base of that privacy fence. And we are looking for the minimum angle of elevation, which would be that red angle theta that I just drew in. I want to solve for an angle. Remember that anytime you're solving for an angle, like an angle is the thing that you want to know, you should be going to an inverse trig function in order to find that thing. We'll want inverse trig function of some kind. in order to figure out what this angle is. So I'll start by setting up an equation that should hopefully contain my angle in it. And if I look at the triangle that I've got drawn in, I know I'm looking for an angle, and I know its opposite side and its adjacent side. If we go back all the way back to SOHCAHTOA, the ratio that's going to use both opposite and adjacent is tangent. So I'll set up a tangent of theta is equal to 9/21. And then solve this thing for theta. That means theta itself should be the arctangent or the inverse tangent of 9/21, which when I plug that into a calculator in degree mode, I get 23.2 degrees. If you got a number that was about like 0.5 or 0.6 or something like that, you put it in your calculator, that almost certainly means that you were in radian mode. And this problem was asking for an angle in degree mode. We'll make sure that we're in degrees for this thing. Also, just about every word problem we do is going to ask for angles in degrees rather than radians. Radians tend to be the more pure math answer. Or if you, yeah, just leave it there. We wanted our answer in degrees, so we'll put our calculator in degree mode. And then, rounding to 1 decimal place, that seems like our best answer is 23.2. This problem has a slight twist on it that's not common to many other word problems. But realized that the way that I wrote this thing, it asks for the minimum angle of elevation in whole degrees so that the rocket clears the fence. So rather than thinking about our usual rules of rounding, which are if it's 0.5 or higher, we round up to 0.5. If it's less than 0.5, we round down. This wants the minimum whole number angle that gets over the fence. So I'm going to argue that no matter what our decimal was, we are going to round up no matter what. Since in this case, 24 degrees gets over the fence, but 23 degrees would not. Right? 23 as the nearest whole number of degrees is just going to be slightly below the top of the fence. So our rocket definitely doesn't get over it. So I'm going to round up to 24 degrees just based on the way the question was worded. I'm eschewing our normal rules for how to round decimals in favor of answering a question that's specific. So 24 degrees for this problem. All right, let's do some more fun with inverse trigonometry. So I want to get the cotangent of the cosine inverse of -63/65. So I want to start by sort of simplifying the conceptual part of this problem. I'm trying to get the cotangent of some angle that I'm going to call alpha. Just the angle that's on the inside of that cotangent, right? Remember that anytime we take the inverse cosine or inverse sine or inverse tangent of a number, my result is an angle. So I'm taking the cotangent of some angle. Just decided to call it alpha because it's the first letter of the Greek alphabet. And the cotangent of some angle is equal to the adjacent side over the opposite side. So if I had some reference triangle, I can just take adjacent over opposite and get my answer that way. Which is exactly what I'm going to try to do. And I'll probably do better than try. So I want a reference triangle for the cosine inverse of -63/65. And anytime I'm creating a reference triangle, I want to make sure that I put that triangle in the correct quadrant. Since reference triangles should usually end up there. And because I'm taking the cosine inverse of a negative number, I should place my reference triangle in quadrant 2. Would you be able to do an example of a bearing problem at some point today? Oh, you betcha. Yeah, it might even be the next problem. Oh, yeah, that'll come after this. But I digress. Back to the thing that we're talking about. Creating this reference triangle. I want to put it in quadrant 2. Again, because I'm taking the cosine inverse of a negative number. And anytime I take the cosine inverse of a negative number, I know I'm going to be in quadrant 2. Because that's just where cosine inverse is defined. So let's draw that triangle. Good thing I've got technology to draw it for me. I'm also going to place the coordinate axes on here to emphasize the fact that this is a reference triangle and it's in the second quadrant. And my specific angle alpha is going to be that guy. I'm more interested in the labels on the sides, though. Cosine is adjacent over hypotenuse. So 63 is my adjacent side, and 65 is my hypotenuse, with an unknown side y. And now, because we are in the second quadrant, my x value should be negative. I'm going to the left. So a negative 63. That also tracks with the negative we saw on the inside of cosine inverse. That negative's got to go somewhere, and I don't ever want to put it on the hypotenuse. That'd have to go on the 63. So this thing's a right triangle, which means I could use the Pythagorean theorem to find my missing side. So let's come over here to y squared plus 63 squared is equal to 65 squared. With the quick note over here that negative 63 squared is the same as positive 63 squared. So I just simplified that negative right away. Oftentimes I find that's helpful since I see a pretty common mistake is putting the negative in there, but then subtracting it incorrectly when it goes over to the other side. So when I go to the Pythagorean theorem, I usually just ignore the negative signs because I know that they're going to get squared away anyway. So I recommend doing that if you're looking at this math. But right, so I want to find y squared, which means I need 65 squared minus 63 squared. And that comes out to 256. If we plug that into a calculator. Don't really expect you to do that in your head. Feel free to use a calculator to get that number. But then if I take the square root of that, 256 is a power of 2, which half of those have square roots. This one has one as well. It is 16. So y is going to be plus or minus 16. And then because we are in the second quadrant, I should take the positive value for y. So y must be equal to positive 16. I'll write that in over here. All right, now that we have a complete reference triangle, I'll use that to answer the original question. It wanted the cotangent value off of this triangle, which again is adjacent over opposite. So negative 63 over 16. So I could put that in the box. Negative 63 over 16. Well, that's our answer. Hey. Oh, I lied about the bearing problem being next. But it's soon. Except next. A few multiple choice questions. Pretty similar to what you'll see on the online part of the exam, but you've probably noticed that the in-person parts of all quizzes and exams don't really have multiple choice on them. So I saved those all for the online half. But you know, we're reviewing for both, so let's just knock these out. All right, I want the exact value of the secant of the arctangent of the square root of 3. So that thing is equal to the secant of pi over 3. Since the tangent inverse of square root 3 is pi over 3. Root 3 being one of the numbers that we have memorized off of the unit circle. So I'll just go to that. Secant. You might not have those values committed to memory, so I'll change it over to something that we should. Secant of pi over 3 is equivalent to the reciprocal of cosine of pi over 3. And that should be something that you can get quickly from the unit circle. This is 1 over a half. And the reciprocal of 1/2 is 2. So option D. After that, the arc sine or sine inverse of the tangent of pi over 3. Nope. Let's try again. The sine inverse of the tangent of 3 pi over 4. It at least had a pi and a 3 in it somewhere. Better at the math part than I am at the talking part, it seems. But the tangent of 3 pi over 4 is -1. So I want to get the inverse sine or the arc sine of -1, which is very similar to asking, you know, what angle on the unit circle has a sine value of -1. And if you went to just the regular unit circle, you'd probably say 3 pi over 2. But that's not correct for arc sine, because remember that when we go into the fourth quadrant, arc sine relabels that entire quadrant to its negative coterminal values. So instead of 3 pi over 2, we should get -pi over 2. Those two angles are coterminal. So they both have a sine value of -1, but only -pi over 2 is a correct answer for the inverse sine of -1. Again, that's important. We've gone over it a few times. But when we end up using this stuff in our calculators, because that's probably where we want to use these inverse trig functions most of the time, it's important to understand what kind of an answer that inverse trig function will spit out. And it is not capable of spitting out 3 pi over 2, but it's very capable of giving you -pi over 2. Yeah. We got up here. I'm confused on the difference between Q3 and Q4. What's the difference between them? Q3 is on the left and Q4 is on the right. That might not be the most helpful, but it is a significant difference between them. So in quadrant. Oh, question 3 and question 4? Aha. So used to seeing Q meaning quadrant. Kind of took off, like that sort of took on a life of its own. So yeah, the difference between questions 3 and 4. Well, there's a lot of different stuff going on. Let's see if chat answered it in a way that was helpful. Yeah, so that's probably the biggest difference is that, yeah, as Savannah mentioned, question 3 is dealing with a value that we don't have off of the unit circle, because -63 over 65 isn't something you'd have committed to memory. So we need a reference triangle in order to find our correct answer. We could also have used a reference triangle in question 4. It would just take more work, and this was meant to be a short question, since that square root of 3 is a value that we'd recognize from the unit circle. So if we have something in the unit circle, we can just take shortcuts to solve the questions a little faster. But a reference triangle would still work. All right, let's take this on to question 6. The exact value or values of the tangent inverse of negative root 3 over 3 is /r. It's just negative pi over 6. This one's got a little bit of a trick to it. Or it's somewhat of a trick question. It's trying to imply that there's more than one answer. But the important part of these tangent inverse of a tangent inverse function and all of the inverse trig functions is that there is only one correct answer to an inverse trig value. That's an important feature of these functions. So we are not going to be looking at multiple values for the inverse trig of any value. It's only ever going to give us one answer. Again, that is a sort of key part of those inverse trig functions, which means that, 5 pi over 6 and 11 pi over 6 is not the correct answer, despite the fact that tangent of 5 pi over 6 and tangent of 11 pi over 6 are both equal to negative root 3 over 3. It is asking a slightly but importantly different question. So the tangent inverse of negative root 3 over 3 is only negative pi over 6. And then what do we got next? The cosine inverse of the cosine of negative pi over 3. Well, let's start by evaluating the cosine of negative pi over 3, which is positive 1/2. Positive 1/2. So negative pi over 3 is coterminal to 5 pi over 3. Both of those angles are in the 4th quadrant, and cosine, being the x value, is positive in quadrant 4. So cosine of negative pi over 3 is positive 1/2, which means the cosine inverse of positive 1/2 is pi over 3. So pi over 3 is our correct answer here. And lastly, triangles ABC and PQR are similar. Find the length of side B. So, if you'll notice, side B isn't labeled on here, but that's okay because we know how to label sides based on the angles that they're paired with. Side B is always opposite angle B. So that means that our side B should be similar to that 8.1. Since those are the similar sides, if I look from one triangle to the other. So I've got B over 8.1 is equal to the only other ratio that I know, which is 2.7 over 3. Or another way of looking at this, if I'm looking at 2.7 compared to 3 being the ratio that I know, triangle ABC is 90% as large as PQR. Since 2.7 over 3 is going to be 0.9. If you prefer to think about it that way. Either way will work, because I then need to solve this thing for B. It is equal to 2.7 over 3 times 8.1, or 0.9 times 8.1. 9 cubed is 729, so this is going to be 7.29. Option C. I fully expect that would be a calculator problem. Don't need to solve that by hand. Okay, the next problem has our bearing on it. Since there's one last multiple choice question that I forgot was on a different page. But going from words about a simple harmonic motion problem to a equation for that simple harmonic motion. So let's read through the question twice. Once just to get the words, second time to pick out the important parts. An object attached to a coiled spring is from its rest moving down a distance of 9 millimeters. Assume the motion is simple harmonic with a sixth of an oscillation per second. The equation that relates the displacement d of the object from its rest position after t seconds is one of these 9 options. Let's go figure out which one. All right, so if I read through the question again, but this time pick out the bits that I think are important. I have this 9 millimeters over here. I know that's going to be related to A. But specifically, that's going to be the amplitude. So the absolute value of A is 9. The other part that's going to tell me what's going on is this line right here. From its rest moving down. That's a description of a negative sine function. From rest moving down. Sounds like negative sine. So with that in mind, I can go get rid of all of the cosine options. So no, it's not going to be a cosine function. Also notice that all of the A values are -9. So I guess I don't really need to worry about that part either. But the reason why I know it's moving down, I know that the amplitude is 9, down is negative, so -9. So I know then it's one of these other 4 functions. The answer is never going to be none of these. So I need to figure out the part that goes on the inside. And that's where I'm going to want to use this sixth of an oscillation per second part. That is telling me that the frequency is 1/6. Right, so if it's oscillations per second, I know that that is a frequency unit. So the frequency is 1/6. If the frequency is 1/6, then the period is 6. And finally, that means that B, which is 2 pi over 6, or 2 pi over the period, ought to be pi over 3. So option E is the one that has pi over 3 on the inside. I'd go with that one. What else? What else? Okay. To someone's question from earlier. The bearing problem. Here it is. So what do we have? A runner begins at the starting line, presumably of a race, and proceeds in a direction of 72 degrees west of north for 3.5 kilometers until she reaches a refueling point, turns 90 degrees southward, running 6.5 kilometers to the finish line. So this must be a 10K. What is the bearing from the starting line to the finish line? And show a mathematical work, draw a fully labeled illustration showing giving bearing size and angles of a bearing is to be found. At least 1 decimal place of accuracy on the solution. Okay, so with all that said, let's construct whatever's going on here. So first things first, I need a starting line. So I'm going to put the start right here. And I'm going to put the compass rose there because I know I'm going to need those. I'm going to need those coordinate axes to figure out what my angle ought to be. So she is going to start by running this race in a direction that is 72 degrees west of north. So if I start at north, rotate 72 degrees to the west. That'll be this angle right here. If you're looking at the angle that's on my ruler, you probably see that that's not 72, but is instead 18, because my ruler is measuring angles from a horizontal line, but bearing angles always get measured from a vertical line. So they get measured either from due north or from due south. So my bearing ought to be this bit right here. Let me just label that before we get too far away. Our initial bearing is this 72-degree angle to the northwest. So, don't forget that west is on the left side of north. West is that way. I don't know. Sometimes I struggle with that. Then we're going to turn 90 degrees southward, which doesn't mean we're going due south. It just means we are going to get to that point, and we can turn 90 degrees either left or right. And southward is going to be a left turn based on the direction that we're going. So I will turn 90 degrees that way, run 6.5 kilometers, and end up at the finish line. So I'll label my finish line. Finish. Right angle there. And I am interested in finding the bearing from the starting line to the finish line. So I'm just going to draw in the rest of my triangle. I don't ever use this color. Let's use it today. Oh, that's why it's a little bit thick. So the angle I'm interested in, bearing from the start to the finish, that'll be this angle down here. I'm going to label it with a beta. Since, bearing, B, beta is a Greek letter. Sounds like it's Greek letter for B. Yeah. So that'll be the angle I'm interested in finding, is that green one. But in order to get there, I'm going to need to solve for some angle that's inside of this triangle, and hopefully that relates to the other two angles. So I'm going to draw in this yellow angle theta, since it's the one that's on the inside of my triangle, and have what kind of looks like a stoplight. Was it on purpose? Was it an accident? I'll let you decide. 3.5 kilometers should have been that distance, while 6.5 kilometers is that distance over there. And I want to find my green angle. So before I start working on the triangle, let's first talk about how I'm going to get that green angle. And I'll want to notice that if I add up my three angles, that red 72-degree northwest bearing, the yellow angle theta that's on the inside of the triangle, and my green angle beta, the one I'm interested in finding, if I add all three of those up, I should get 180 degrees, since those three angles together connect north to south, or half of a circle. So I just rely on some geometry to come up with that equation. I'll just need to get, if I knew what theta is, that yellow angle, I could use it to solve for beta, my green one. So I'm going to do exactly that. Go back and look at the triangle that we just drew. I know my opposite side and my adjacent side. It seems like all of these problems come back to tangent somehow. But opposite and adjacent together would be tangent. So tangent of theta should be opposite over adjacent. So 6.5 divided by 3.5. Meaning that theta itself is the arctangent or tangent inverse of 6.5 over 3.5. And we just need to plug that into a calculator. I got 61.7 degrees. Since we said we could just round up one decimal place on this one. So then we've got to go find our bearing. The angle in our bearing, which is beta, should be 180 minus 72 minus 61.7. Which toss all of that in a calculator and hopefully you get 46.3 degrees. So the last step is to just put that angle into a bearing. If I'm going from my starting line to my finish line, I am traveling southeast. So my bearing should contain a southeast. So this is 46.3 degrees. Southeast. Yeah, I told you I was going to do that. That's southwest. Yeah, 46.3 degrees west of south. Right. From the start to the finish, that's a direction of southwest. Could I explain how it'll be either 90 or 180 again? Sure. After drawing your picture, if your angles added together make a straight line, that's 180 degrees. But if your angles added together only make up a single quadrant, that'll be 90 degrees. So my three angles added together make a straight line. They go from north down to south, making it 180. I'm just looking for something in the geometry of the triangle that I drew to relate either to a straight line or to just one quadrant. This thing spans two quadrants, so 180 degrees. Oh, that's why. Okay. I just cut this page out. Cool. I said I cut worksheet 8 out, so why don't we skip that line? I'd also said that I skipped that. So let's bring it down to this. Further explaining why I didn't have any of that information over there. Since I've got just a second, zoom out here, realized that I don't have part of what I wanted on the review. So I'm just going to copy and paste something over real quick. Oh, fine, be like that. This one. Open. All right, so in just a moment, we'll be calculating a reference triangle, but I wanted to put some reference material on that triangle. Hey, I got a moment to take some questions from chat. No, worksheet 8 is not on the in-person exam either. It is not. Okay. I meant for it to be there, but then I just forgot to write it in. So, bank error in your favor. If you're familiar with Monopoly. Why wouldn't you be? It's a popular game. Okay. Back to the stuff that we're working on. All right, did that load in? Oh, it hasn't loaded in yet. Well, if it does decide to load in, I've got the supposed to be loading in. Well, we'll just keep working without it, and hopefully it'll pop in a minute. So right, what are we doing here? We are looking for all solutions for theta in radian measure. So it's going to be probably important to highlight that. All solutions for theta. That means I'm going to want to be adding 2k pi to my answers. So I'm just going to go down to the answer box and just write a plus 2k pi in there so I don't forget it later. If I want all solutions, not just solutions between 0 and 2 pi, that means I'm going to want all coterminal angles to this thing as well. So starting off with the cosine of theta being equal to -5/7. In particular, pointing out that cosine is equal to a number that is less than 0. So I want to find solutions that are in quadrants 2 and 3. So in quadrant 2, my solution angle is equal to pi minus some reference angle. And in quadrant 3, my solution angle is equal to pi plus some reference angle. Oh, that's why. I just put it next to the wrong problem. So I feel like it should have loaded by now. Let me bring that down. There we are. So that information I borrowed from worksheet 4 or worksheet 11. I think it was listed in both. But for each of those equations to know which quadrant to go to and how to solve for the angle, here they all are on the right. We want the ones out of quadrants 2 and 3, so pi minus and pi plus the reference angle. All right, enough of that. Let's go actually calculate that reference angle. Which we should get our reference angle theta is equal to the cosine inverse of positive 5/7. Right, since the reference angle is always a positive value being plugged into our inverse trig function. And if we go to a calculator in radian mode, we should get 0.7752. If you got a number that was like, I don't know, 60 or something, that probably meant you were in degree mode, but we're looking for answers in radians this time. So we'll go with that. Then take to a calculator again to do pi minus 0.7752. And you should hopefully get 2.3664. And then sticking with our calculator, pi plus 0.7752. And I got 3.9186. So those are my two answers that are between 0 and 2 pi. So I will go put those in my answer box. And then also add 2k pi to each. To get every angle that's coterminal to either one of those, since they also solve the problem. 129. All right. Let's keep trying to be quick about this. So anytime I'm looking for a reference angle, I always want to be taking the inverse sine, inverse cosine, or inverse tangent of a positive number. So because it's the reference angle, that's why I went with that. So when are you going to write 2k pi and when are you not? Depends on the beginning of the question. So like in the one down below, the one that we'll get to here in a minute, is asking for all angles between 0 and 2 pi, which means I don't need all coterminal angles. I just need the ones I'll find on the unit circle. Versus the question above asked for all solutions for theta, not just the ones between 0 and 2 pi. All right, we gotta keep moving. So I know that I want plus 2k pi in this box as well, so I'll write that in. All right, record speed, let's do this. 5 sine of theta minus sine theta tangent theta equals 0. Notice that I've got I have a sine of theta in both of these two terms, so I'm going to factor it out. Sine of theta times 5 minus tangent theta is equal to 0. So I get two options. Either sine theta equals 0, right? Or 5 minus tangent theta equals 0. And I'll start working on solving those two. Off the left, that's just the unit circle. Theta is either equal to 0 or pi. So I can just drop those two answers in the box. Cool, left side's done. Onto the right side, 5 minus tangent of theta is equal to 0. It means that tangent of theta must be equal to 5, with 5 being a positive number. So the two quadrants I'm going to want to look in are 1 and 3. Since those are the two quadrants where tangent is positive. So I should get a reference angle. Theta ref is equal to the arctangent, or tangent inverse of 5. Which if I plug that into a calculator, I get 1.3734. 0.3734. So then my solutions are theta equals the reference angle, and theta equals pi plus the reference angle. Meaning 1.3734 and pi plus that number, which I got 4.5150. So those two also go in the box. And all of these are plus 2k pi. And there we go. Interestingly enough, not that you need to answer it this way, but these answers could all simplify to just k pi and 1.3734 plus k pi. Not a simplification that I'll be expecting, but you could do it if you wanted to. So I know I'm over on time, so if you've got another class to get to, feel free to leave. I'll be posting this review video later, but I do have one more page, and I think I can hold the classroom for about 5 minutes. So I'm going to do that to try to finish this review all in one video. So if you want to stick around, feel free. I'm going to keep going over it, but I'm also not going to be, I won't be insulted if you leave right now. Bye.
Multi-choice question be on test.
On the online part, yes, not on the written part. Yeah. Question was, would there be multi-choice answers on the test? And yes, for the online part, no for the in-person part. All right, let's do this last page real fast. So what do we got? Cotangent squared plus 3 cosecant theta equals 3. I've got too many trig functions in my equation. I have cotangent and I have cosecant. So I'm going to use a Pythagorean identity to change cotangent squared of theta to cosecant squared of theta minus 1. And leave the rest alone. Minus 3 equals 0. I'm also going to pull the 3 over. Meaning I've got cosecant squared of theta plus 3 cosecant theta minus 4 is equal to 0. And then that equation factors, or that expression factors, to cosecant of theta minus 1 times cosecant of theta plus 4. Giving me two equations that I can solve. Either cosecant of theta equals 1, or cosecant of theta is equal to negative 4. And solve that thing for theta. If cosecant of theta is 1, that means that sine theta is equal to 1 over 1, or theta equals pi over 2. So I'll toss that answer in my answer box, pi over 2. On the other side, cosecant of theta is equal to negative 4, which means that sine of theta is equal to negative 1 over 4. And I'll need a reference angle for that thing. It's negative, so I want answers in quadrants 3 and 4, since those are the two where sine is negative. Ooh, and I'll also need a reference angle. So that reference angle, theta ref, is the inverse sine of positive 1/4. Which when I plugged that into a calculator, I got 0.2527. And then to get the correct answers, I need pi plus that reference angle. And 2 pi minus that reference angle. Plugging it into a calculator, I got 3.3943 and 6.0305 respectively. 3943 and 6.0305. Gotcha. So this time I was only asked to find answers between 0 and 2 pi. So I don't need all my coterminal angles. I just need the two angles that are between 0 and 2 pi. All right. And lastly, oh yeah, this is a fun one. Secant of 5 theta is equal to square root 2. I want to find all answers between 0 and 2 pi. So let's start by saying that if secant of 5 theta is equal to square root of 2, that means that cosine of 5 theta is equal to 1 over the square root of 2, which is root 2 over 2. So I get two options for theta. Or yeah, I get two options for 5 theta. Either 5 theta is equal to pi over 4, or 5 theta is equal to 7 pi over 4. And because I've got that number out in front of theta, I'm also going to say anything coterminal to these answers will also solve it. And I need that because I need to find some specific answers that are in here. So keeping this thing going. This means theta is going to be equal to pi over 20 plus 2k pi over 5. Or if I get a common denominator, this will be pi plus 8k pi over 20. On the right side, theta is equal to 7 pi over 20 plus 2k pi over 5, or simplifying to 7 pi plus 8k pi over 20. Then because this thing was 5 theta, I know I need to list out 5 solutions for each of those two equations. So starting at pi over 20 for the left equation and 7 pi over 20 for the right equation, I'll list my the next 4 for each of those. So I'm counting by 8s, which means my next one is going to be 9 pi over 20. And then add 8 to get 17 pi over 20. Add 8 again to get 25 pi over 20. And add 8 one last time to get 33 pi over 20. And then just shrink that a little bit so they all fit in the box. All right, and now do the right side. Still counting by 8s, this time just starting from 7. I'll get 15 pi over 20. Add 8 again to get 23 pi over 20. Add 8 again to get 31 pi over 20. And one last time to get 39 pi. over 20. And then just notice if I added one more, I'd be over 40, which means I'd be beyond 2 pi. So I don't need any more of those answers. All right, and that's the end of the review. Cool. So I know I've got some questions in chat. Let me go see what's going on in there. So answering some of these, what did we have going on? Yeah, that is kind of a lot. You're not wrong. Yeah, problems I'm currently working on are from worksheet 11. So anytime I've got these equations, those are worksheet 11. All the word problems are coming from worksheet 10. And all of the basic inverse trig stuff is worksheet 9. Hi.
So I'm only getting 2 answers, but it looks like they want. I'm just not seeing where those other answers could be.
Gotcha. So the step right here where we cancel the cosine on both sides.
Doesn't work.
So it does and it doesn't.
Okay.
It just means that because cosine could be 0, you don't necessarily want to cancel them out. Instead, you would have wanted to factor cosine out of the equation.
Okay.
So basically what it means is that we're missing solutions where cosine is equal to 0.
Okay.
So if you add in pi over 2 and 3 pi over 2, it should work.
Okay, thank you.
Okay. How can you know when to use 2k pi versus when to use reference angles? So that's kind of a false dichotomy there. Because sometimes because we could use 2k pi and reference angles in the same problem. So we go to reference angles anytime we've got a value that we don't know from the unit circle. That's when reference angles are important to us. And then the 2k pi versus not 2k pi is mostly just about the statement of the problem. If it asks only for solutions between 0 and 2 pi, we don't need all of our coterminal angles. But if it asks for all solutions for theta, then we want to add 2k pi. All right, what's up? Can I start setting up? Oh yeah, sure. I'm sorry. It's I'm usually not around here this late. Okay, let's see here. Pull this guy out. Pull this guy out. And close that down. It's signed me out. All right, cool. It is all yours. Okay. So 7 pi over 4 came from the other angle where cosine of theta is equal to root 2 over 2. Oh. All right, what do we have going on over here? Still available for help on Thursday. Yeah, sure. I can be available for help on Thursday. Just send me an email. And I'll do what I can to set something up. Back to the second to last page. Sure. Second to last page. That was this one, right?
No, like, they. We did not, no.
5 minutes to my next class.
And we're not, we don't have these.
Oh, I don't usually meet anywhere for help on Thursdays because I'm normally Monday and Wednesday are my office hours. So if we're doing Thursdays, it'll be probably a Zoom meeting. So you just want to send me an email and we'll set something up. For sure, you are welcome. And I've probably kept this video going a bit longer than I meant to, but I am gonna stop the recording here. So good luck on the exam.